So next we have this thing called the factor theorem, which I think intuitively we all know this already, right? Look at it. I think this makes a lot of sense here. C is a zero of p of x if and only if x minus c is a factor of the polynomial, right? That's how we find the zeros sometimes. We factor our polynomials, set it equal to 0, and find the zeros that way. The division algorithm actually allows you to prove it. I mean, one direction you don't need the division algorithm, okay? If x minus c is one of the factors, your polynomial is x minus c times some quotient. If you plug in c to that, you're going to get 0 times the quotient is 0. So if x minus c is a factor, this is why we solve them the way we do. If x minus c is a factor, then x equals c is one of the zeros. The other directions where you need the remainder theorem. Okay, so the division algorithm tells me if I want to divide my polynomial by x minus c, I'm going to get x minus c times a quotient plus some remainder. And if my remainder is 0, okay, remember p of c, in this direction we're assuming c is a 0, so if p is a 0, the remainder would be 0, and we would get that indeed p of x can be factored into x minus c times q of x. Okay. So, say not a profound result, a very important result, but pretty obvious, I think. If you can factor x minus c out, then c equals one of your zeros. We use that to do this type of problem also sometimes in the reverse direction. We did one of these in a previous section. Use the factor theorem to find a polynomial with roots x equals 2, x equals negative 1, and x equals 4. Express the answer in standard form. Okay. So the previous theorem said if c is one of your roots or your zeros, x minus c needs to be one of the factors. And so we usually just want to set up the simplest one we can here. Our polynomial could be x minus 2 to get x equals 2 as one of the zeros, x minus a negative 1 or x plus 1 to get the negative 1, and then x minus 4. If I set each of those to equal to 0, I get 2, negative 1, and 4. You can multiply by anything else, but if we want the simplest one, it would be x minus 2 times x plus 1 times x minus 4. Okay. Now this question says explicitly express in standard form. That's the a sub n, x to the n, plus all the other terms. I have to multiply it out. Okay. And so we have to just do this brute force. I did one before that had an x minus 2 and an x plus 2, and I did those first because the middle term drops out. I don't get that here, so I'm just going to multiply the first two of them together. So I get x times x is x squared, and then I get a minus 2x, and then I get a 1x, so that'll be minus x, and then minus 2 times 1 will give me minus 2. So if I FOIL that out, I get x squared minus x minus 2. The two middle terms are minus 2x plus x, gives me a minus x. But then I still have to multiply by x minus 4. And now if you rely on the FOIL acronym, they do in algebra sometimes, the first, outer, inner, last, that doesn't work when you have more than two terms on one of them. But FOIL is really just a good way to remember to do all the terms times all the terms. What I have to do is every term in x squared minus x minus 2 times every term in x minus 4. And you could do it in either direction. I could do x squared times both terms, minus x times both terms, negative 2 times both terms. I usually like to do the smaller one though. That's what I've done here. I've done x times all three terms. So x times x squared gives me x to the third. X times negative x gives me negative x squared. And then x times negative 2 gives me negative 2x. And then I move on to the next one, negative 4 times all three terms. So I get negative 4x squared, and then negative 4 times negative x will give me plus 4x, and then negative 2 times negative 4 gives me plus 8. And then you can combine like terms if you have any. So we have the x to the third. Let's see, on x squareds we have negative 1, negative 4, so negative 5x squared. On the x terms we have negative 2 and 4, so that gives me 2x and plus 8. Okay. So the real work on this problem is multiplying it out. The factor theorem makes it kind of trivial to write it in factored form, but then we got to do the work to multiply it out. And we're going to conclude with something that I'm going to be brave and say is probably a little bit outdated, but it's still in the books. I'm going to cover it here. Extremely useful if you have to solve a lot of polynomials by hand, but with modern technology we have lots of software ways we can solve them. But if you think about this historically, people had to solve equations and they didn't have calculators and computers to help them out, so it was nice to be able to rule out some potential answers. And this is still useful to be able, if you have to solve some and you want to find whole number answers, it's a nice way to rule out a lot of answers. So the rational root test, sometimes it's called, or the rational zero test, given a real polynomial p of x, so a polynomial p of x where its coefficients are real numbers, with degree n and actually integer coefficients. Okay, that's an important part of this. The rational roots, so rational roots are rational numbers that can be written as ratios of integers, p over q. If they exist, they must be in the form p over q, where p is a factor of the constant term, the one on the end, and q is a factor of the leading coefficient. Okay? So, and p over q must be written in lowest terms, like 1/2 instead of 2/4 or something like that. I have here a little explanation of why this works out. If you think about it, if you want to get p over q as one of your solutions, that comes from a term qx minus p. Okay? And I could have n of those, so I've written them out here if you think about multiplying this out. But so if you look at my first term, q sub 1 x minus p sub 1. If you set that equal to 0, you're going to get p1 divided by q1. So I'd have a p over q with subscripts of 1 there. The next one will give me p2 over q2, and so forth. So if my terms look like that, if you think about what happens when you multiply stuff out, you get all the middle terms are a mess, but the leading term comes from multiplying all these q's together. Okay? And then the constant term comes from multiplying all the p's together, all the constants there. And then you have all the middle terms in between. So if you look at that, every single one of these q's is going to divide the leading term here, and all of the p's are going to divide into the constant there. So that's all the rational root test is telling me. And here's one application of it, okay? So list the possible rational roots. We're not going to solve it. We're just going to list the possible rational roots. And it's also possible that it doesn't have any rational roots, but it will eliminate infinitely many numbers from the list and give me a list of possible rational roots. Okay. So by the theorem, any rational roots, they have to be of the form p over q, where q is a factor of 5. Okay? Q is a factor of the leading coefficient, and p is a factor of 12, the constant. This is nice when one of those numbers is prime. There's not a lot of factors here. The factors of 5 are just 1 and 5, and they could be positive or negative. 12 has quite a few factors. Okay? 12 could be 1 times 12, 2 times 6, or 3 times 4. So we have all of those factors. And the rational root test says they're all going to be one of these numbers divided by 1 or one of these numbers divided by 5. Okay? So my possible rational roots are plus or minus on all these things. 1, 2, 3, 4, 6, and 12 if we divide by 1, or each of those divided by 5. Okay, so that's still what? 1, 2, 3, 4, 5, 6, 12 possible rational roots, which seems like a lot, but out of infinitely many numbers in the real number system, we narrowed it down to 12 possible roots. Okay. It could be irrational roots, but this tells us of rational roots. These are the only possibilities. So, as I say, with modern technology, maybe not as useful as it used to be, but it's still used quite a bit in algebra when you have the problem of trying to find rational roots by hand.